You're flying from Frankfurt to Paris, aboard a Boeing 737 today. The captain pushes two levers forward. The engines roar to life. Fully automatic. A digital system called FADEC controls the fuel supply. The ignition, the throttle, the temperature, and the pressure. Everything coordinated, perfectly synchronized. You might be thinking, modern technology, but you'd be wrong. This system was invented way back in 1942 by BMW in Munich. And it was called the Kommandogerät, or Engine Management Unit. The BMW 801 Kommandogerät was the first integrated engine control system in aviation history. A single lever controlled 9 different engine parameters simultaneously: throttle, mixture, propeller, supercharger, ignition, cooling flaps, oil cooler, temperature, pressure, all automated, all coordinated. 83 years later, every modern airliner uses the same concept. Boeing 737, Airbus A320, Boeing 787, Airbus A380. All of them use FADEC, Full Authority Digital Engine Control, the digital version of that German Kommandogerät from 1942. This isn't speculation, it's documented through technical reports, through Operation Paperclip, through patents, through the history of modern aviation itself. Today, I'm going to show you the technological lineage, from the BMW 801 to the Boeing 787, a direct connection, spanning more than 8 decades, and you'll understand that modern aviation wasn't invented in Seattle. It was developed in Munich in 1942. The BMW 801 Kommandogerät was, technically speaking, a revolution. To understand why, you need to know how airplanes were flown before 1942. Imagine you're a pilot in a P-51 Mustang. You want more power. What do? You move the throttle. Good, but now the engine's running too lean, so you have to adjust the mixture control. Now the supercharger isn't optimally set. You adjust the supercharger lever. The propeller pitch is wrong. You adjust the propeller lever. The ignition timing is too early. You tweak the ignition. The engine's getting too hot. You open the cooling flaps manually. 6 different levers. 6 different settings. Each one has to be perfectly coordinated, or the engine could explode, or lose power, or overheat. In a dogfight, you might have 5 seconds. An enemy fighter's coming up behind you. You have to evade, accelerate, climb, and perfectly coordinate 6 levers while you're shooting, while you're navigating, while your life depends on it. American pilots had a saying: watch your back, monitor your instruments, verify your settings. The cockpits were complicated, dangerous, deadly for inexperienced pilots. Many planes crashed, not from enemy fire, but from pilot error, engine failure, due to incorrect settings. The British had the same problem. The Spitfire was a brilliant aircraft, but the cockpit was a nightmare. Dozens of levers, switches, gauges. Pilots took months to learn everything, and even then, they made mistakes. And then came 1942. The BMW 801 engine, with its Kommandogerät, was installed in the Focke-Wulf FW-190. For the first time, German pilots flew an aircraft with only one power lever. One lever. That was it. You wanted more power? One lever forward. The Kommandogerät coordinated everything automatically. Throttle opens. Mixture enriches. Propeller pitch increases. Supercharger switches to a higher stage. Ignition timing is optimized. Cooling flaps open depending on the temperature. All automatic. All perfectly synchronized. A German FW-190 pilot could concentrate on the fight, while a Spitfire pilot was still wrestling with 6 different levers. This wasn't just convenient, this was a tactical advantage, a survival advantage. The technical specifications of the BMW 801 D2 were impressive. 41.8 liters of displacement. 14 cylinders, 2 rows, radially arranged, 1,700 horsepower takeoff power at 2,700 revolutions per minute. But the revolutionary thing wasn't the power, it was the control. The Kommandogerät used a mechanical computer system based on cams, levers and linkages. It continuously measured engine temperature, pressure, RPM and airspeed. And it adjusted, automatically, in real time, without pilot input. The engineering achievement was extraordinary. The Kommandogerät weighed only 51 pounds, but it contained over 300 precision-engineered parts. Every part had to be accurate to within 1/100th of a millimeter, every tolerance critical, every connection perfectly tuned. BMW developed the system between 1939 and 1941. 3 years of development time, hundreds of prototypes, thousands of test hours. The engineers solved problems that no one had addressed before. How do you mechanically coordinate 9 different functions? How do you make it reliable? How do you do it in a vibrating, rotating aircraft engine? The solution was brilliant. A main cam that rotated with the power lever position. From this cam, mechanical linkages went to 9 different subsystems. Each subsystem had its own cams, levers, and feedback mechanisms. When the pilot moved the lever, the main cam rotated. That activated the throttle, but at the same time, it also activated the fuel pump and the propeller governor and the supercharger, all simultaneously, all in the right proportion. But it wasn't just simple translation. The Kommandogerät had feedback loops. It measured the actual engine temperature. If the temperature was too high, it automatically reduced the fuel supply, even if the pilot had the lever all the way forward. The system protected the engine from the pilot. That was revolutionary. Other aircraft had simple translations. Lever move flap directly mechanically, but with no intelligence, no protection. If a pilot made a mistake, the engine exploded. The BMW Kommandogerät had built-in safety limits. It couldn't overload the engine. It was physically impossible. The mechanical interlocks prevented it. Take a look at the functions. The pilot moves the power lever. The Kommandogerät receives the signal. Immediately, the sequence begins. First action, throttle opens proportionally to the lever position. More air flows into the engine. Second action, fuel supply increases automatically. The correct mixture is maintained. Not too rich, not too lean, perfect. Third action, propeller pitch is adjusted. At low power, shallow angle for maximum thrust. At high power, steeper angle for efficiency. Fourth action, supercharger switches between stages. Low altitude, first stage. High altitude, second stage. Automatically, fifth action, ignition timing is optimized, depending on RPM and load. Earlier at low load, later at high load. Sixth action, cooling flaps, open as needed. If the engine's too hot, the flaps open. If the engine's optimal, the flaps close. Less drag. Seventh action, the oil cooler is regulated, temperature kept constant. Too hot, more cooling. Too cold, less cooling. All of this happened automatically, in fractions of a second. Coordinated, perfectly tuned. An American P-51 pilot had to do all of that manually. Each setting individually, each adjustment consciously, every mistake deadly. A German Focke-Wulf FW-190 pilot moved one lever and focused on the enemy. The tactical advantage was immense. German pilots reported the FW-190 was easy to fly. Even inexperienced pilots could master it. The Engine Management Unit, EMU, handled the complex engine control. The pilot flew and fought. British pilots noticed this quickly. By 1942, the FW-190 began to dominate the Spitfire. Not because the engine was more powerful, but because the pilot was more effective. less distracted, more focused, more dangerous. In the summer of 1942, an FW-190 was accidentally landed in England. A German pilot mistook a British airfield for a German one. He landed, was captured, and the British had a perfect specimen. Immediately, the tests began. British test pilots flew the FW-190, and they were shocked, not only by the performance, but by the cockpit. Captain Eric Brown, the most famous British test pilot, wrote in his report, "The cockpit layout is brilliant. A single power lever controls the entire engine. Incredibly simple, incredibly effective. The Royal Air Force wanted to copy the system immediately, but there was a problem. No one understood how it worked. The Engine Management Unit, EMU, was a mechanical wonder. Hundreds of precision parts, cams, levers, gears, linkages, all microscopically precisely manufactured, all perfectly tuned. British engineers disassembled the Engine Management Unit, EMU. They drew every part, they measured every tolerance, and they realized, we cannot build this. Not with our manufacturing technology, not in this war. German precision mechanics were too advanced, the tolerances too tight, the complexity too high. The Americans tried as well. After the landing of the FW-190 in England, the British shared all the information. A complete Engine Management Unit, EMU, was sent to Wright Field, Ohio. The best American aircraft engine engineers examined it for months. Their conclusion, revolutionary, but impossible to replicate during the war. The manufacturing costs would be astronomical, the production time too long, the complexity too dangerous for mass production. So American and British pilots continued to fly with their complicated cockpits, 6 levers, dozens of switches, hundreds of possible error combinations. While German pilots moved one lever, BMW produced more than 61,000 BMW 801 engines between 1942 and 1945, each with an Engine Management Unit, EMU. It was the most produced German radial engine of World War II, not because it was the most powerful, but because it was the most reliable and easiest to use. FW-190 pilots loved their aircraft. The machine responded perfectly. No matter the altitude, no matter the speed, no matter the attitude, the Engine Management Unit, EMU, ensured that the engine always ran optimally. Compare that to Allied engines. The American Wright R-2600 Cyclone in the B-25 bomber had constant problems, overheating, cylinder cracks, engine failure. Why? Because pilots had to coordinate the settings manually and made mistakes. Constantly. The British Rolls-Royce Merlin in the Spitfire was brilliantly designed, but dangerous to operate. Pilots had to monitor the boost pressure manually. Too much pressure, engine explodes. Too little pressure, too little power in combat. It was a constant balancing act. The BMW 801 with the Engine Management Unit, EMU, didn't have these problems. The system prevented overstressing automatically. If the pilot demanded too much power, the Engine Management Unit, EMU, limited it. If the temperature rose too high, it reduced the power automatically. The engine could not be overloaded. It could not overheat. The system protected itself. That meant German engines lasted longer. Aircraft returned more often. Pilots survived. Missions were successful. The numbers prove it. The FW-190 had one of the lowest loss rates of all German fighters, not because it was faster than anything else, but because it was reliable. Because the Engine Management Unit, EMU, protected the engine. Because pilots could focus on the fight, not on engine management. In the winter of 1944, the Americans realized we must have this technology. But how? The war was coming to an end. Germany was losing, and Operation Paperclip began. Operation Paperclip was the largest technology transfer program in history. Between 1945 and 1959, the United States brought more than 1,600 German scientists, engineers, and technicians to America, officially to use their knowledge, unofficially to prevent the Soviets from getting it. The operation began in May 1945. American troops advanced into Germany. Special units had lists, names of scientists, addresses of research centers, locations of factories. Goal: secure German technology. Before the Soviets get it? In Munich, they found the BMW aircraft engine factory, partially destroyed by bombing raids, but the design offices were intact. Thousands of technical drawings, hundreds of prototypes, dozens of engineers. The Americans packed everything up, drawings in boxes, prototypes on trucks, engineers in jeeps, heading west, away from the Soviet zone. An American officer wrote in his report from June 1945, "German aircraft engine technology is at least 5 years ahead of us." The automatic engine control system of the BMW 801 is particularly impressive. We have nothing comparable. The list of Operation Paperclip recruits was impressive. Werner von Braun, rocket engineer, later director of the NASA Marshall Space Flight Center, responsible for Saturn V, the moon rocket. Kurt Tank, chief designer of Focke-Wulf, designer of the FW-190, consultant for American fighter aircraft development. Hans von Ohain, inventor of the German jet engine. Went to Wright-Patterson Air Force Base, worked on American jet engines, and dozens of BMW engineers. The men who had developed the Engine Management Unit, EMU. Their names are largely unknown, classified for decades, but they were there, in American labs, at American research centers. They were not treated as prisoners of war. They were hired as valued consultants, with good salaries, with American passports. They had a mission: teach us what you know, and they did. The Soviets tried the same thing. They occupied the eastern zone of Germany. They also found BMW factories in Eisenach. There, they continued production under Soviet control, with German engineers using the same technology for the Red Army. It was a race, East versus West. Who would get more German expertise? Who would develop faster? Who would dominate post-war aviation? America won that race, not through force, but through incentives. German engineers chose the West: freedom, better pay, more modern research facilities, the chance to continue their research. At Wright-Patterson Air Force Base, Ohio, the Americans established a special laboratory. German engineers worked there, analyzing the engine management unit, not to copy it, that was still too complicated, but to understand the concept, the principle. The realization was clear: integrated engine control is the future. A system that automatically coordinates all parameters. That's the way forward. But how do you build that? With 1940s technology, it was impossible. The engine management unit worked mechanically, with precision parts. The Americans couldn't replicate that in mass production, so they waited for new technology. In the 1950s, the first electronic control systems arrived: vacuum tubes, transistors, relays, primitive electronics. But sufficient to build simple automatic controls. American jet engines began using electronic regulators, but only for single functions: fuel supply or temperature regulation. Not integrated, not coordinated like the German engine management unit. In the 1960s, transistors became smaller, more reliable, more powerful, and American engineers started to develop more complex systems, inspired by the German engine management unit, but electronically. The first real FADEC system was developed in the early 1970s for the Pratt & Whitney F100 engine used in the F-15 Eagle fighter jet. It was called Digital Electronic Engine Control, DEC. The development lasted from 1970 to 1974. Pratt & Whitney invested $50 million. Hundreds of engineers worked on the project, and many of them had German mentors, men who had come from Germany in the 1950s and 1960s through Operation Paperclip. These German engineers brought the engine management unit concept with them. They explained integrated control is the key, not separate systems, but a coordinated system that optimizes all parameters. The Americans listened and adapted the concept for electronics. The DEEC system had sensors, temperature sensors on every part of the combustion chamber, pressure sensors in the turbine, speed sensors on the compressor, fuel flow sensors at the injection point. Dozens of sensors, all connected to a central computer. The computer was primitive by today's standards, a digital computer with 8 kilobytes of memory, less than a modern calculator, but sufficient for the task. What did it do? Exactly what the BMW 801 engine management unit had done in 1942. It automatically coordinated all engine parameters: fuel, ignition, temperature, pressure, everything. But now, electronically, with sensors, with computers, with digital precision, the F-15 pilot had one power lever. The DC system did the rest automatically, perfectly tuned, optimal for every altitude, for every speed, for every maneuver requirement. The tests were impressive. F-15 pilots reported, "The aircraft responds perfectly. No matter what I do, the engine always delivers optimal performance. I don't think about engine management anymore. I just fly." Sound familiar? It should. Because that's exactly what Focke-Wulf FW-190 pilots said 30 years earlier. The BMW engine management unit, only now digital, only now electronic, but conceptually identical. The DEC system had an advantage over the mechanical engine management unit. It could learn. It had programmable software. If engineers found optimizations, they could update the software. The mechanical system was fixed. What was built was built. But the basic idea, that came from Munich. From BMW in 1942, NASA documented this in technical reports from the 1970s and 1980s. They cited German wartime technology as inspiration. They analyzed the engine management unit principle. They adapted it for modern electronics. It was not a copy. It was an evolution from the mechanical German system to the electronic American system. But the basic concept was identical. In the 1980s, FADEC became the standard. Every new jet engine got a full authority digital engine control system, military jets, then commercial aircraft, Boeing 737, Airbus A320, all of them. Today, no modern commercial aircraft flies without FADEC. It's mandatory for safety reasons, for efficiency reasons, for reliability reasons. And every FADEC system does exactly what the BMW 801 engine management unit did in 1942. It automatically coordinates all engine parameters. It optimizes performance. It protects the engine. It relieves the pilot. Take a look at modern examples. Boeing 737 MAX uses CFM International LEAP 1B engines. Each engine has a FADEC system. The system has over 250 sensors. It processes data at a frequency of 1,000 times per second. It automatically adjusts fuel supply, compressor position, turbine cooling, and thrust vectoring. All coordinated, all optimized. The pilot, he moves 2 levers, forward for takeoff, back for landing. The FADEC does everything else, automatically, exactly like the engine management unit in 1942. Airbus A320, the largest passenger aircraft in the world. 4 Rolls-Royce Trent 900 engines, each with its own FADEC. The system controls 97% of all engine functions automatically. The pilot only controls thrust direction and thrust level. The rest, automatic. Boeing 787 Dreamliner, General Electric Gen X engines, state-of-the-art FADEC technology. The system communicates with the aircraft computer. It optimizes fuel consumption based on flight profile. It reduces emissions. It extends engine life. All automatically, all intelligently. All based on the Engine Management Unit principle from 1942. The numbers are impressive. A modern FADEC system reduces fuel consumption by 15% compared to older systems. It lowers maintenance costs by 25%. It increases engine reliability by 40%. And it makes pilot error in engine control virtually impossible. Why? Because it implements the BMW principle, integrated control, automatic optimization, built-in safety limits. The technological lineage is documented. BMW 801 Engine Management Unit 1942, Operation Paperclip 1945 to 1959, German engineers in American labs, the 1950s and 60s, the development of electronic engine control in the 1970s, FADEC as the aviation standard from the 1980s to today. 83 years, a direct connection, from Munich to Seattle, from BMW to Boeing, but it goes further than just airplanes. The concept of integrated engine control is everywhere. In your car, modern cars have engine control units, ECUs. What do? They coordinate fuel, ignition, valve timing, turbocharger boost automatically with one gas pedal, just like the engine management unit, only for a car, not for an aircraft in ships. Modern ship engines have electronic control systems, diesel engines, turbines, all utilizing integrated control. One lever, everything else automatic. In power plants, gas turbines for power generation, controlled by integrated electronic systems, temperature, pressure, RPM, fuel, all coordinated automatically. The principle is universal, and it was invented in Munich in 1942. This technical truth is uncomfortable for some. America would like to believe that modern aviation was invented in Seattle, but the documentation shows something different. German innovation, American adaptation, global implementation. The facts are clear. The first integrated engine control system was developed in Munich in 1942 by BMW for the Focke-Wulf FW190. It was called the Engine Management Unit, and it worked brilliantly. After the war, through Operation Paperclip, this technology came to America. German engineers brought their knowledge with them. They taught their American colleagues. The concept was adapted for jet engines, for electronic systems, for the modern era. Today, every airplane utilizes this principle. FADEC, Full Authority Digital Engine Control, the digital incarnation of the BMW Engine Management Unit. 83 years of evolution, but the basic concept unchanged. One lever controls everything. The system coordinates automatically. It optimizes, it protects, it unburdens. This is German heritage. In every Boeing, in every Airbus, in every modern aircraft, worldwide. If you appreciate this technical history, if you want to understand how modern technology really originated, then support this channel, because these stories are often not told. They're uncomfortable, they contradict the narrative, but they are true and they are important. Technological history is complex. It crosses borders. It ignores national myths. It shows the reality. Innovation comes from everywhere. It is shared. It evolves, and it benefits the whole world. The BMW Engine Management Unit is a perfect example. German engineering created it, American technology digitized it, global aviation uses it. Everyone benefits. The BMW engineers who developed the Engine Management Unit are largely forgotten. Their names aren't in history books, no monuments, no honors. But their technology flies every day, in every commercial airplane, worldwide. Think about that. Every time a Boeing 787 takes off, every time an Airbus A320 lands, every time millions of people fly safely from one place to another, they are using German technology from 1942. The FADEC system in a modern Boeing 737 MAX costs about $500,000 per engine. It's one of the most complex electronic systems in the aircraft. It has dozens of sensors, multiple redundant computers, millions of lines of code. But the basic concept, one lever controls everything automatically. That's the BMW 801 Engine Management Unit. 83 years later, digital, but conceptually identical. The irony is perfect. Boeing, the American symbol of aviation, is using a German concept from World War II in every single aircraft. Without the Engine Management Unit principle, there would be no modern FADEC. Without FADEC, there would be no modern commercial aviation. Imagine this. Pilots would still have to coordinate 6 different levers today, while controlling an aircraft with 300 passengers during takeoff, during landing, in an emergency. It would be impossible. Too dangerous. Too complex. The Engine Management Unit principle made modern aviation possible, safe, reliable, efficient. And it was invented in Munich in 1942 by BMW engineers who dared to take a radical approach, a single lever, everything else automatic. The world has changed since then. Technology has evolved, from mechanical to electronic, from analog to digital. But the basic principle remains the same. Integrated control, automatic coordination, optimal performance, maximum safety. That's the legacy of the BMW 801 Engine Management Unit, not as a relic, but as a living principle, in every modern machine, in every aircraft, in every car, everywhere. The next time you fly, think about it. The captain moves 2 levers forward. The engines start. Fully automatic. FADEC makes it possible. But FADEC is BMW Engine Management Unit, digital, modern, but at its core. Munich, 1942. This isn't speculation. This is documented history. Operation Paperclip brought German engineers to America. They shared their knowledge. America developed it further. The world benefits today. That's technological transfer. That's how civilization progresses. Ideas cross borders. Wars end, but knowledge remains, and it evolves. Some call it theft. America stole German technology, but that's too simplistic. Yes, Operation Paperclip was systematic. Yes, German innovations were transferred. But without the further development by American engineers, the Engine Management Unit principle would have remained a brilliant mechanical system. Too complex for mass production, electronics made it universal, accessible, standard. That was the American contribution, but the original idea that came from Munich, from BMW, in 1942. That should be recognized, not to glorify a war, but to honor technical truth. German engineering made a fundamental contribution to modern aviation. The Engine Management Unit was revolutionary, and its principle lives on today, in billions of machines, worldwide. If you're ever sitting in a modern airplane, look at the cockpit. See the 2 power levers. Know this, that simplicity was made possible by German innovation, by BMW, by the Engine Management Unit, by a radical idea from 1942. One lever for everything, automatically coordinated, perfectly optimized. That's the legacy. That's the technological lineage. That's the truth. BMW 801 Engine Management Unit 1942, FADEC 2025. Same idea. 83 years of evolution, a direct connection. Modern aviation thanks Munich, whether it admits it or not.